right, so question 17 should be, I mean, you're definitely going to have at least one or two questions like this, pretty straightforward, right? We've got ammonium sulfide solid breaks down to give us ammonia gas and hydrogen sulfide gas, right? In our equilibrium expressions, solids don't show up, right? We ignore liquids and solids. So equilibrium constant would just be the concentration of ammonia times the concentration of hydrogen sulfide, right? So it's not A, right? It's not C, it's not D, it's not E. Right, so none of the above, right, for question 17. And then, yeah, we'll use this to answer question 18, all right? And we did one in class kind of like this earlier yesterday when we talked about the kW of water. And we're going to solve this kind of the same way because they tell us this equilibrium constant equals 1.26 e to the negative 2. They want to know what is the concentration of ammonia, right, at equilibrium. You might think you don't have enough to answer this question, but we do. We do have enough to answer this question because we know our equilibrium constant, right? My equilibrium constant is 1.26 e to the negative 2, right? My concentration of ammonia and my hydrogen sulfide, we're going to get that from the balanced chemical equation, right? Because for every 1 mole of ammonia that forms, I'm going to form 1 mole of hydrogen sulfide, right? Right from the stoichiometry of that balanced equation, we can see they're formed in equal amounts, right? So if I did this reaction and made 10 moles of ammonia, I'm making 10 moles of hydrogen sulfide. So if I call ammonia X, I can also call hydrogen sulfide X because they are the same concentration. They're formed in the same amount, the same rate. So that makes this equation, right, X times X. So we get 1.26 e to the negative 2 equals X squared, right? Square root of both sides, and X equals 0.112 maybe. Just going from memory earlier today, so 0.0126. Yeah, 0.112 would be my concentration of X, which is, right, that's my concentration of ammonia. That's also my concentration of hydrogen sulfide. Both of them would be that 0.112 molar for question 18. And again, we can make that jump because we know the stoichiometry and we can ignore the ammonium sulfide because this is a solid. We can ignore that. We don't have to worry about that concentration, right? Otherwise, we'd have, two unknowns. We'd have to figure out this and these. We don't. We just have these two, but they're the same, so we can call them X for question 18. All right, question 20. All right, a lot of questions on question 20. A lot of people came up to office hours and just said, we guessed. I guessed on question 20, didn't know. A lot of people thought this was Le Chatelier's problem or Le Chatelier's principle in this question. What kind of question is question 20? What do we have to do for question 20? Not all at the same time here. Yeah. Grace. Excellent. Yes. Thank you. You're paying attention today. Yeah, this is a Q question. This is not Le Chatelier's principle, right? Le Chatelier's principle would be, we have this at equilibrium and I change the pressure, I change the temperature, or I add more nitrogen, or I add more ammonia. What direction does this shift? right? That is a Le Chatelier's principle question. We have this at equilibrium and we make a change to it, right? We wouldn't need to know concentrations if this was Le Chatelier's principle. This is a reaction quotient question, which is Q. And our reaction quotient, right, is the same. It's products over reactants, except for our reaction quotient can be done at any time, any concentration, and it tells us a direction. It tells us what direction the reaction wants to move. So just like I would set up my equilibrium constant for this reaction, right? My equilibrium constant would be the concentration of ammonia squared times the constant, or all over the concentration of nitrogen times the concentration of hydrogen cubed, right? We don't need to know that. We don't need to do that because they already tell us the value. At equilibrium, the value is 4.34 e to the negative 3. So we're not at equilibrium, right? We have these concentrations and we want to know what direction the reaction will move to reach equilibrium. So Q would be done the same way, concentration of ammonia that we have squared divided by the concentration of nitrogen times the concentration of hydrogen cubed, right? Plug in our values. I've got 1.93 squared divided by 1.02 times 1.97 cubed, right? Do some calculations here. 1.93, we square that, divide that by 1.02 times 1.97, raise that to the third. All right, and I get a Q, and maybe I made a mistake, but we get the same answer. I get a Q equals 4.77, 4.78. All right, so what does that tell us about this reaction? Right, our Q, correct, yeah. Our Q is greater than K. How do we get that, right? We got that because I must have a higher concentration of products than I want at equilibrium. So the reaction must want to move to the left. We must want to move the reaction to the left, forming more reactants. As I form more reactants, right, my concentration of product will go down, my concentration of reactants will go up until Q equals K. So yeah, we're beyond equilibrium, right? Because Q is greater than K. So does that kind of help like what we're looking for? Yeah, Emily, I can do that too. But quite a few people came to me thinking this was Le Chatelier's principle when, Le Chatelier's principle would be, here's our system at equilibrium. We do one change to it. So yeah, Emily, K, it's the same calculation. Q and K are the same calculation. K is equilibrium and only equilibrium concentrations. Q, we can use concentrations at any point in time in the reaction. And we use this value, right, in conjunction with K to basically say, where is this reaction? So we need to be told K, right? We're told that K is 10 to the minus 3. We calculate Q and we see, it's 10 to the minus 1. So that's larger. So how did this number become larger? It became larger because I have more products, right? I've got more product than I want at equilibrium and less reactant. So this number is larger. This number is smaller than I normally want it. So Q greater than K, we're beyond equilibrium. So to get to equilibrium, we're going to have to shift this to the left. Does that help, Emily? And correct, it's reactants because our reactants are on the left, and products are on the right side of the reaction. Yeah, Lila. So K, I know we've got a lot of Ks, right? When we're dealing with equilibrium, it's going to be a Kc, it's going to be a Kp. When we get to acid base, we'll talk about Ka, we'll talk about Kb. When we do solubility, it'll be a Ksp. If you were looking at the binding constant of a drug, it would be the Kd. All of these values of K for equilibrium are unitless. So when we're dealing with equilibrium, K and our equilibrium constants, our equilibrium expressions, K is unitless. And if we take a note, right, oops, this is a capital K. When we were doing kinetics and we were writing our rate law, right, our rate laws were like rate equals the rate constant times the concentration, you know, this times the concentration of this value of this K, our rate constant K, which is a lowercase k, that has units, right? So rate, our rate constant K has units. Equilibrium, our equilibrium K is a capital K, even though I didn't do a good job of drawing it as a capital K in all these cases. This is unitless. Yeah, Ezrin, we're going in numerical order here. So we did 10 and 12 a while ago. All right, 20, 21. Okay. So 21 is an example of Le Chatelier's principle, right? Which of the following reactions would increase pressure at constant temperature, change the concentration of reactants and products? And in order to change the concentration, right, if we increase pressure, we have to have different moles on both sides, right? If the number of moles in the gas phase are the same on both sides, pressure wouldn't have an effect. So if I increase pressure, I favor the side, right? Increase pressure. And it's not asking what direction this is going, but increased pressure favors the side with fewer moles in the gas phase, fewer moles, smaller volume, right? They can occupy a smaller volume. So if I increase pressure, right, I've got 4 moles here versus 2 moles here. So I'm going to push that equilibrium to the right. I've got 1 mole versus 2 moles. So increasing pressure would shift that equilibrium to the left. I've got 3 moles versus 2 moles. Increasing pressure would shift that equilibrium to the right. And then I've got 3 moles versus 2 moles again. So increasing pressure would shift that equilibrium to the right as well. And so because it's only asking for a change in concentration and not asking directionality, right? All of these reactions, the equilibrium would be impacted by a change in pressure. A reaction where that wouldn't be the case would be like hydrogen. This is the one I gave you in class, right? Hydrogen plus bromine goes to 2HBr. Oops. Right. So there I've got 2 moles versus 2 moles. An increase in pressure would not change this equilibrium because I've got equal amounts of gas on both sides of the reaction. So yeah, I think that, Giselle, that answers your question, right? So if the moles are the same on both sides, correct. It would have no effect on equilibrium. I could change it, I could increase it, I could decrease it, wouldn't matter, wouldn't change my equilibrium. right, question 23, I guess, is next. How many transition states and intermediates are there in this reaction, right? Our transition states are energy maximum. So there's one transition state, there's two transition states, there's three transition states. Our intermediates are in between the transition states. So here would be one intermediate, and here would be a second intermediate. So we have three transition states, right? And two intermediates in this reaction. A is our starting material, G is our product. So those don't count as a transition state or an intermediate, right? There are reactants and products. For 23, 24. Right. What would the slowest step? So the slowest step is the step that has the highest activation barrier. All right. The slowest step, oops, not what I wanted to do. Slowest step. Think of them, right? Activation energy. Think of them as hills, right? The higher the hill, the longer it's going to take for you to walk up there. So the slowest step of the reaction has the highest activation energy. And we can take the reaction left to right. We can also take the reaction right to left. And so if we do that, right, actually the slowest step, right, our activation energy is the energy between where we start and our transition state. So, right, there is my activation energy for that first reaction, right? Here is the activation energy for my second reaction, right? My third reaction's got a small activation energy. But if I take this reaction in reverse, right, G all the way up to F, that is actually the largest activation barrier. That's a larger hill, G to F, than A to B or C to D. So that would be the slowest step in this reaction, right? If we were running it forward, if we were able to run it either direction, forward or backwards. So yeah, choice D here, right? G to F would be the slowest step. All right, 25 is our last question. Must have been on the bottom here. Oh, okay. So yeah, question 25 is kind of like that other version of the half-life question that I was talking about earlier, where you can't just use a nice round half-life and do that, 20, 40, 60, there's our half-life. Here, we actually have to calculate it. So they tell us the rate constant for the reaction is this. How long will it take for the technetium to decay to 1% of its original activity? And somewhere in here, they should tell us that it is a first order. Yeah. So it's first order. So we know natural log of concentration time t equals negative kt plus natural log of my initial concentration. And this is where we can just do our percentages as decimals, right? To make our life a little bit easier. Times 0, I have to have 100% of this material. And I'm looking for when do I have 1% of this material. We can't plug in, we don't want to plug it in as a percentage though. We want to plug it in as a decimal. So times 0, I've got 1. And I'm looking for what point do I have 0.01 of that sample left. So we can plug that in. Natural log of 0.01 equals my rate constant, 1.925 e to the negative 3. Inverse minutes, I think someone asked this earlier, right? If they give it to you in minutes, just leave it in minutes, right? There's no need to convert it to seconds and make more work for yourself. times time, we're looking for time, and then natural log of 1. All right, the natural log of 1 is 0, so that disappears. The natural log of 0.01 is like negative 4.60 5 equals negative 1925 e to the negative 3. All right, divide by our rate constant, negative 1.925 e to the negative 3. Negative 1.925 e to the negative 3 inverse minutes. And we get a time for this reaction of, divide that by negative 1.925 times 10 to the minus 3. I get something like 2,329 or 392 minutes, right? Again, pay attention, it's asking for it in 4 sig figs, so I would just say, 2.392 e to the 3 minutes, right? Keeping it in minutes. And I apologize, I was doing blue on top of blue there, not really the easiest to see. Yeah, so Camille, how do you tell the initial concentration is 1? We're looking for what time does it get to 1%, and so time 0 has to have 100% of the material, right? We haven't started the reaction at time 0, right? That's when we're starting the reaction, is time 0. At time 0, the reaction hasn't started yet, so we should have 100% of that material or 100% of that activity of that. And then to give it a real number, we just turn 100% into a decimal to say, okay, that represents 1. And we're looking for 1%, which as a decimal would represent 0.01. The reason why I like that is because it makes our life easier, because the natural log of 1 is 0. And so basically, once we get past that, it just simplifies our calculation. But we can always make that assumption, because at time 0, you should have 100% of what you have. No, Ezra, it won't always ask for a percentage, right? I could have said, I could have said this concentration, here's my rate constant, what's the time? Or, if this is my concentration and this is my concentration in the future, this many seconds in the future, what's my rate constant? So no, it won't always ask for a percentage.